Hey everybody, welcome back. Okay, so in this video, I'm going to try to keep this one short. We're going to talk about X-ray production. Since now we have the idea of energy levels, we can understand what a typical X-ray spectrum looks like. So first of all, what's the conventional way to produce X-rays? Well, in an X-ray tube, you accelerate electrons across a pretty big voltage difference, tens of thousands of volts. They slam into a target. In the process of them losing energy in collisions, very high energy photons are emitted in the X-ray portion of the spectrum. And that's what you see indicated in this little picture, the electron accelerating to the left and then hitting the target and these X-ray photons being produced. Okay, so here is a typical spectrum that you see right here. Its intensity, which you can think of as number of photons on the vertical axis, and then wavelength of the X-rays on the horizontal. And the first thing I want you guys to see is there's always a minimum wavelength. It might be hard to see with the resolution of the video right here. Okay, and if we go to our course page, I have a right here. You can look at another X-ray emission spectrum. This is of molybdenum, and make it a little bit bigger. Okay, now you'll see again intensity on the vertical, wavelength on the horizontal. These are for different accelerating voltage differences. So you can see right, this is 5 kilovolts, 10,000 volts, 10 kilovolts, 15, 20, 25. And you'll notice that there's always a minimum wavelength. So let's talk about that first. So if I accelerate these electrons, and this is a nice review again of accelerating particles between plates. So here's my filament, right, where the electrons are coming from. So this will be at a low voltage, this will be at the higher potential. My accelerating voltage is V. Remember, if I'm assuming these electrons, when they're ejected off of this hot filament, they're going to be moving relatively slowly compared to their final speed when they slam into this plate. So I'm going to assume that the initial kinetic energy is essentially zero. So the change in the kinetic energy is, to a very good approximation, just going to be the final kinetic energy, big KF, when they arrive here. Okay, now remember that the change in kinetic energy is going to be the absolute value change in the kinetic energy is going to be the absolute value of the charge of the electron, which is the fundamental charge, 1.6 times 10 to the minus 19 coulombs, times the voltage difference that you're accelerating the electrons across. So that's going to be the tube voltage in the X-ray tube, V. Okay, now suppose that all of the kinetic energy of the electron is lost in the formation of one photon. That would be the most energetic photon possible. Okay, now it's much more likely though that when this electron collides into the metal, that it loses its energy through several photons. So it doesn't just lose all of its energy in the formation of one photon. In fact, there's a German word for this radiation. It's called Bremstrawling Radiation, which means breaking radiation. So there'll be several photons emitted of various energies as a single electron slows down in the metal. But there is a chance that all of the kinetic energy is lost in the form of one photon. That's going to be the most energetic photon. So the maximum photon energy of an X-ray photon that's going to be emitted is when all of the kinetic energy of the electron, right, is converted to one photon. So the maximum photon energy is going to be the fundamental charge times the voltage difference. Well, remember, energy of a photon is hc over wavelength. So the maximum photon energy has a corresponding minimum wavelength, right? Because the wavelength's in the denominator. And this has to equal E times V. Oh, so look, we can actually find that the minimum wavelength of the X-rays is going to equal hc over E times V. So the only thing it's going to depend on is the tube voltage. hc and E are constants. In fact, if you want, you can remember that hc can be written as 1243, and I'll put the units in brackets because it can get confusing that we have a unit abbreviated EV, and in the formula we have an EV, which is the product of fundamental charge and voltage difference. Okay, so you can write this equation like that. All right, so notice that what's going to determine the minimum wavelength is the tube voltage, and only the tube voltage. It's an interesting result because it doesn't depend on actually what type of metal target you're using. Okay, it just depends on the tube voltage. All right, so that's what you see right here in the summary notes. But also, if I go back to this spectrum, you can see that as the tube voltage increases from 5,000 volts to 10,000 volts, etc., that minimum wavelength is getting shorter and shorter, as predicted. Okay. This smooth curve, these smooth curves that you see, that's characteristic of that Bremstrawling radiation that you're getting, that most of the electrons are producing or giving many photons of different wavelengths, all longer than the minimum wavelength. Now, what I want to draw your attention to, though, is when you get to a sufficiently high enough tube voltage, in this case 25,000 volts, you start to see the formation of these very narrow peaks. These are called the characteristic lines or characteristic radiation lines. Where these occur in wavelength does depend on the type of metal target you're using. That's why they're called characteristic. And they're labeled, it's hard to see, but K alpha and K beta. That's an K sub alpha and a K sub beta. So where are these coming from? What's giving rise to these very narrow, sharp peaks at these particular wavelengths? That's where the idea of atomic energy levels comes in. And this is really cool. What happens is, if you have enough tube voltage, so the electrons are moving really fast, the K shell electrons, now the K shell, right, that's N equal 1. So these are big metal atoms. The K shell, that's the first shell. So these electrons are really deep in the electron clouds, right? They're the closest electrons to the nuclei. What'll happen is a incoming electron will actually deliver enough energy that a K shell electron on the atom is ejected. Well, now you have a vacancy, right? Now you have an available state. So one of the higher electrons in the atom, in a higher state, will make a transition to that available state. In the process, a photon is emitted because it's an atomic transition. You have a transition of an electron from a higher state to a now vacant lower state. And that's what gives rise to these photons, the K alpha and K beta photons. Okay? If the transition is from an N equal 2 electron, a so-called L shell electron, that's what actually gives the that's what gives the K alpha photons. Okay? And from the higher shell, the N equal 3 shell, down to N equal 1, so that's an M shell electron. If there's a transition of the M shell electron to the K shell vacant state, that gives rise to the K beta. K alpha is more probable. So, in fact, when you have these X-ray tubes that are built for commercial use, you really are using the K alpha photons. That's how they're designed. And that's pretty much one wavelength coming out of these tubes if you do some filtering. Okay, so you can do some filtering so that you basically are selecting these K alphas. Oh, one last thing before I go. Notice that the K alpha photons have a longer wavelength than the K beta. That makes sense because the alpha transition is from n equal 2 to n equal 1. That's a lower energy transition than the K beta. The K beta, that's a transition from n equal 3 to n equal 1. So that's going to be a more energetic transition, a higher energy photon, and therefore a shorter wavelength photon. Okay, so you should know what gives rise to these characteristic X-ray, sometimes called lines, because the peaks are so narrow. These are transitions from higher shells to the n equal 1 shell, because when the electron slams into the metal, one of the n equal 1 electrons is ejected. It's really cool. And again, we can understand the formation of these lines once we have the idea of energy levels in allowed states. Okay, that's it for X-ray production. I'll see you in the next video where we talk about laser operation, which is another another way up. It is an application of the idea of atomic energy states, or molecular states for that matter. I'll say more about that in the next video. Okay, bye-bye.